In this video, we're going to look at one final relationship between our electric field and our potential difference V. So remember, back in the start, we in general had defined our electric field as being equal to negative the integral of E dot dl. Okay, so what we can do with this equation is we can take the derivative of both sides. So let's say take the derivative of both sides. So what we get on the left is just dv, and on the right we're going to get rid of that integral and we're just going to have negative E dot dl. Okay, well, our E is going to have an x component, a y component, and a z component, as is our dl. And so what I'm going to say here with x, y, and z is we're going to assume Cartesian coordinates just for simplicity, but we could do the same thing in spherical or cylindrical. So let's just say assume Cartesian coordinates. So this E, or rather negative E dot dl, would then become negative our x component times dx minus our y component of the field times dy minus the z component of the field times dz. And so we can call this equation 1 to be consistent with the notes. So now if we take a closer look at this left side, we know from multivariate calculus that if we want the total change in V, so multivariate calculus, if we want this total change in V, then that's equal to the sum of the partial changes with respect to our three components. So total change in V, and so again we're just going to assume Cartesian for simplicity, so it's V, x, y, z, is just the sum of our partial changes with respect to each of those three components. So with respect to x, y, and z. So in other words, we can say that dv is equal to the partial of v with respect to x dx plus the partial of v with respect to y dy plus the partial of v with respect to z dz. And so to be consistent with the notes, I'm going to call this equation 2. And so what we can do now is we can basically compare our equations 1 and 2. So because we know that these two things are equal, so here we've sort of expanded our dv, and up here we sort of expanded the right side, so we know that ultimately this expression here is equal to this expression here. And so what we can see is that we have, for instance, negative ex being multiplied by dx in expression 1, and down here we have partial of v with respect to x multiplied by dx. So similar things for negative ey and partial of v with respect to y, negative ez and partial of v with respect to z. So what we can say then is that our electric field is equal to negative the gradient of our voltage. And so that's just based on knowing our gradient relationship from our previous vector calculus unit. And so where does this negative sign come in physically? So of course mathematically it's easy to see that yes, we have a negative sign there. So we would say, for instance, our E of x is equal to negative partial of v with respect to x, whereas in our normal gradient equation, of course, we had positive signs. Well, the negative sign is basically just saying that the direction of E is in the opposite direction of increasing voltage. So let's just write that out briefly. So our negative sign in the equation is indicating that our direction of E, so direction of E is opposite to the direction of increasing voltage. And so that makes sense because if we think about a voltage increasing between 2 points, so for instance, if we have a point here and a point here, and our right point is more positive than our left, we know in general our electric field is pointing in the direction that our positive charge would want to move. So we would have our electric field in this case in this direction. So because of that difference in direction of increasing voltage and electric field direction, That's where that negative sign out front comes from. And so ultimately what this boxed equation does is it's giving us another way to get our electric field apart from Coulomb's or Gauss's law directly. So if we have a V expression, so this is useful mostly when V is known, because then we can find our E instead of going back to a previous equation or re-deriving from Gauss's law or from Coulomb's law. And so if you want to see some examples and get some practice using that equation, you can look on page 148 in the textbook. Example 4.2 will give you some practice. And if you have any questions as you're working through that example, definitely let me know.